In this video, we work a couple of extra examples regarding Rolle's theorem. We're asked to determine whether Rolle's theorem applies on a given interval, and if the theorem applies, we're asked to find the x values that are guaranteed to exist by the theorem. So we have this function, and we're on this interval, and the question is, does the theorem, does the theorem apply? So here's our theorem. It says, let f be continuous on a closed interval from a to b and differentiable on the open interval from a to b, and suppose that the function values at a and b are the same. Then there exists at least one x value on the open interval from a to b such that f prime evaluated at that x value is 0. So basically it says as long as the function is continuous on the interval and differentiable on the interval of interest, and the y values are the same at the endpoints, then we're guaranteed to have at least one x value where the derivative is 0. Now, since we're starting and stopping at the same place, our y values are the same on either side. We would have to, if our function changes, if it's a non-constant function, if we allow the function to increase for a little bit, in order to get back to that location, it has to decrease. So we would be guaranteed a relative max in that case. Now, if our function decreases from the beginning, and then it increases again to get back to that y value, we would have a relative min. And of course, that can happen multiple times over the interval. But basically, our theorem says that we're guaranteed at least one x value where that happens, and it might be a relative max or a relative min. We just don't know which one it is. And when we achieve that relative maximum or minimum, it's going to be nice and smooth because the derivative exists. The derivative is 0. So the tangent line at the top or the bottom will be a horizontal tangent line. Okay, so that's what we're dealing with. So we're looking at this particular function. The question is it continuous? And we say, yes, it's absolutely continuous. This is just a cube root function. We know that functions involving radicals and composite functions involving polynomials and radical functions, all of those are going to be continuous. Basically, all the functions that you've studied in your earlier courses are continuous. We know polynomials are continuous, rational functions are continuous on their domains, all your trig functions are continuous on their domains. The root functions, square root, cube root, fourth root, fifth root, all of those are continuous on their domains. You just have to think about domain issues. But here we've got a function with a rational exponent, and we know that rational exponents correspond to root functions. So this is a composite function. We've placed a polynomial inside a root function, essentially. And that is definitely continuous on its domain. Now, since we're taking a cube root, since we've got a 3 in the denominator, since that function is well defined for any number x that we substitute here, because we can take the cube root of a positive number or a negative number, and we always get a number out. We get some number between negative infinity and infinity. And that's going to be true anytime that integer in the denominator, whenever you have a rational exponent, is odd. The input can be any positive or negative number, and the output will exist whenever we are taking a cube root or fifth root or seventh root or any nth root where n is odd. Okay, so let's state it. We said f is a composite function involving a rational function, or that's not a rational function, excuse me, a polynomial and a function with rational exponents. Yes, technically we've multiplied it by -1 and added the 4 as well. So it's a sum of a composite function and that. But I think that that's sufficient. That implies that f is continuous on its domain. And that implies that f is continuous on the interval of interest. Okay. So the first part of our theorem is satisfied. The function is continuous on the interval. And the next question is it differentiable? Well, let's compute f prime. And this is the derivative of a sum or difference of functions. The derivative of 4 is 0, and then the derivative of this requires the chain rule. So we're going to have a -1 times, well, the derivative of the outside function. So I see I've got an x minus 1 inside and a u to the 2/3 function. This is my inside function. And then my outside function is that power function raising an expression to the 2/3 power. So you say, okay, well, what's the derivative of a function raised to the 2/3 power? It's 2/3 times the original function raised to the 2/3 minus 1. 2/3 minus 1 is 2/3 minus 3/3. 2/3 minus 3/3 is -1/3. Then you put the original inside function back inside and multiply by the derivative of the inside by the chain rule. Just remember the chain rule says take the derivative of the outside evaluated at the inside and then multiply by the derivative of the inside. The derivative of x minus 1 is just 1. And so we've got f prime is equal to this -2/3 times x minus 1 to the -1/3. Now this can be a little bit misleading if you don't remember what that -1/3 power means. You might say, okay, isn't that just the same as what we started with? We have a composite function involving a polynomial and a rational exponent. So shouldn't it be fine? If this function f prime is well defined everywhere, then the function is differentiable? We say, yes, but that negative exponent, remember, corresponds to an expression in the denominator. So if you have x to some negative power, that's the same as 1 over x to the same power but positive. So this is really -2/3 times 1 divided by x minus 1 to the +1/3. And if we wanted to, we could write that with radicals. X to the n divided by m is the nth root of x to the n. So this 3 in the denominator means we're taking the third root of x minus 1 to the first, or just x minus 1. So that's -2/3 times 1 divided by the third root of x minus 1. And if we multiply straight across, we've got a -2 in the numerator and a 3 times the third root of x minus 1 in the denominator. And the question is that function well defined on the interval from -26 to 28? You say, no, I'm going to have a problem when the denominator is 0. F prime is undefined when x is equal to 1, because the denominator would be 0 when x is equal to 1. So we'll say f prime is undefined when x equals 1. And 1 is in the interval from -26 to 28. So that means that f is not differentiable in the interval of interest. So the theorem does not apply. Now we can see this visually if we graph the function on Desmos. This is actually a really popular function. It actually reminds me of birds. You know, you ever draw those little birds when you were a kid? Like, here's some clouds, and there's like a tree. The clouds in my tree look the same, don't they? And then you've got birds like just sort of flying everywhere. This x to the 2/3 kind of looks like that. So I've taken x to the 2/3, I've shifted it 1 unit to the right, and then I flipped it upside down and added 4. So I'm going to end up with a curve that looks roughly like that, but it's been shifted and it's been flipped, and then we added 4 to it. So that's what I think of whenever I see this function. Let's look at it in Desmos and confirm that my memory is accurate with regard to my little bird function. So here's our function. If we're looking at it on its entire domain, the domain is all real numbers. So from -infinity to infinity, we get something that looks like this. Again, it's just a transformation of y equals x to the 2/3, which looks like that. But again, we've shifted it 1 unit to the right, we flipped it upside down, we added 4, and that's how we got the other function, this new function. But we're not interested in the whole thing. We're only interested in the part of the function on the interval from -26 to 28. So I'm going to change this to a dotted line. And I actually like to make it a little bit thinner when it's dotted. But this is the part of the function that we're interested in. Now, the theorem says if the function is differentiable and continuous on the interval and the y values are the same at the endpoints, then the theorem applies. Well, if we evaluate the function at -26 and +28, we find that the y values at both of those points are -5. We could have done that on paper. We chose not to because we checked differentiability first. First, we said it's continuous because it's a composite function involving a polynomial and a function with a rational exponent. And so we said that part was satisfied, but the differentiability requirement was unsatisfied. So if we actually compute that derivative, like we did on paper, we get x equals -2 divided by 3 times the cube root of x minus 1. And I don't know how to do cube roots on Desmos. So I just write that as something to the 1/3 power instead. So this is actually what our derivative graph looks like. Notice that we've got a vertical asymptote on the derivative graph when x equals 1. A little bit easier to see if we zoom in. I'll make that a dotted line as well. So we see the derivative does not exist at that sharp corner. And then we can also just look at the derivative graph. We see that that function does not exist, or that the derivative function has a vertical asymptote at x equals 1. So the slope as we approach x equals 1 from the right looks like it's going to infinity. And the slope, or I said from the right, but I meant the left. And the slope as we approach x equals +1 from the right is going to -infinity. So when we look at the original graph, again, just that part of it that we're interested in, we can see that the slopes are positive to the left of 1 and negative to the right of 1. So the theorem does not apply. But the function is continuous. Since the function is continuous, and we start at a y value equal to -5 and we end at a y value equal to -5, we do have a relative maximum on that interior. We just don't have a relative maximum at a point that corresponds to sort of a smooth location, a point where the derivative is well defined and the tangent line is horizontal. The curve has a little cusp there at x equals 1. If we wanted to, we could evaluate the function at x equals 1. I think we can see just from looking at the form of the function that we're going to get a 4 there. Yeah, and that's our relative maximum. So the function has a relative max of 4, or actually an absolute maximum of 4 on the interval of interest. And it occurs at x equals 1. All right, so that is an example where the theorem doesn't apply, and we're able to visualize it. Let's look at another example. So here we have another example. We've got a rational function on a particular closed interval. We're asked to determine whether Rolle's theorem applies. Well, rational functions are continuous on their domains, but we have to make sure, well, actually, I'm sorry, that our interval does not include any x values that cause the denominator to be 0 when the numerator is non-zero. Because if our interval of interest includes any x values that cause the denominator to be 0 when the numerator is non-zero, then we've got a vertical asymptote, and then we have a discontinuity. We'll say, well, this function is potentially discontinuous when the denominator is 0, and the denominator is 0 when x equals 1. Now, when we substitute x equals 1 into the numerator, we can find out if that numerator is also equal to 0 at x equals 1. So let's evaluate the numerator at x equals 1. I've got 1 squared plus 3 times 1 minus 5. So that's 4 minus 5, which is -1. So the numerator is -1 when the denominator is 0. So f of x equals 1 is a vertical asymptote of the function. And x equals 1 is on the interval of interest, the interval from 0 to 1. So the function is discontinuous on the interval of interest. And if the function is discontinuous, that means the theorem does not apply. All right, let's visualize this function on Desmos. So here's our function. It's kind of cool, actually. It's x squared plus 3x minus 5, all divided by x minus 1. So it has a vertical asymptote at x equals 1. Now, we didn't talk about that on paper, but we could show, since the degree of the numerator is greater than the degree of the denominator, the function has a slant asymptote. And that's because the degree of the numerator is exactly 1 more than the degree of the denominator. It has a slant asymptote, and you can find that slant asymptote using long division. Actually, I think I'll show you how to do that. So since the degree of the numerator is 1 more than the degree of the denominator, it's the degree of the denominator plus 1. F has a slant asymptote. And you can find that using long division. So we have x minus 1, and we're dividing that into x squared minus or plus 3x minus 5. So we just ask ourselves, well, x times what will give us this x squared? X times x will work. So we put an x up here above the x term, and then we distribute this x to the x minus 1. X times x is x squared. X times -1 is -x. And then we subtract, but when we're subtracting polynomials, we just add the opposite. So we would distribute that negative to each term and then collect like terms and columns. So we'll have x squared minus x squared, which is 0x squared, and then a 4x minus 5 here. And then we'd start over and we'd say x times what gives us 4x? Well, just a plus 4. 4 times x is 4x, and 4 times the -1 is a -4. And we're subtracting. So we change the signs and add like terms and columns. 4x minus 4x is 0x, and then we have a -5 plus 4, which is -1. Now, since the degree of -1, which is just a constant, is 0, and the degree of x minus 1 is 1, since this degree is less than this degree, then we stop. This is called the quotient of our long division problem, and this is called the remainder. So the original function, x squared plus 3x minus 5 divided by x minus 1 is equal to the quotient plus the remainder over the original divisor. In this case, that's x plus 4 minus 1 divided by x minus 1. Now, this function here that we get for our quotient is called the slant asymptote of this function. It's just a line, y equals x plus 4, and our function is going to get very, very close to this line as x goes to positive or negative infinity. Because as x goes to positive or negative infinity, this term is going to go to 0, and but this piece won't. But our function will approach that line. This is a slant asymptote. I should write the rest of it down. So there's our slant asymptote, and we're only interested in the interval from 0 to 2 though. So this is the entire graph. But on the interval from 0 to 2, we're just right here. So let's make this dotted as well. And that's the part we're interested in. Now, if we are determining whether Rolle's theorem applies, we usually look at the function values at the endpoints of the interval. So we say, well, what is the function value when x equals 0? Turns out it's 5. And what is the function value when x equals 2? It also turns out to be 5. So that part is satisfied, but the function is discontinuous. So since the function is discontinuous, we are not guaranteed to have any x value on the interval from 0 to 2, where the derivative would be 0. Now, this particular function I think is pretty interesting, because normally what I do in this case is I try to change the interval. I say, okay, well, what could I change the interval to so that the theorem would apply? Well, it turns out I can't. Uh, I love making up these homework problems, the questions. So you say to yourself, okay, I want the y values to be the same at a and b. I want to have an interval that does not include x equals 1 because the function has an asymptote at x equals 1. And so I need to avoid x equals 1. So that means either I'm going to be to the left of x equals 1 or to the right of x equals 1. But if you look at those branches, check it out. That function is increasing on the interval from negative infinity to 1. And it's also increasing on the interval from 1 to infinity. So there's no way that I can choose a couple of x values to the left of x equals 1 so that the y values are the same. And there's no way that I could do the same thing on the right of x equals 1. So to the left or to the right, I'm not able to choose an interval so that Rolle's theorem will be satisfied. So I think this is a really good example. Of course, Rolle's theorem is not satisfied for this particular function on this particular interval because the interval includes x equals 1. But when you ask yourself, can I modify it so that the theorem does apply? In this case, we really can't because the function's increasing on both branches, and therefore the y values are never the same. And if the y values aren't the same, we can't use Rolle's theorem. You might say, well, if that's true, is there another theorem that we could use instead? It turns out there is. That's called the mean value theorem, and we'll discuss that in the next set of videos.